Good evening everyone and welcome to my presentation. Let me introduce myself. I am Kopitha from Swinburne University of Technology. It's my great pleasure to present today on towards amine-based carbon dioxide capture in cement-based materials. As all of us know, carbon dioxide emissions are increasing and it causes several environmental effects such as global warming and climate change. Statistics show that main source of CO2 emission is from building operation and building materials. Among that, cement production causes 8% of global carbon dioxide emissions. There are many strategies to reduce the carbon dioxide emissions such as usage of supplementary cementitious materials and adapting carbon capture and utilization. However, all these approaches are not applicable for existing buildings as we are living in the concrete jungles. It's better to find a way to capture the carbon dioxide using existing structures. Now our question is how to capture the carbon dioxide using existing structures. This leads us to the new concept called direct air capture using some kind of coatings on the existing buildings. This would capture the carbon dioxide from the environment and then penetrate into the cement-based materials and form stable calcite. As we have enough surface area to apply the coating on the buildings, it would capture more carbon dioxide similar to the trees. In the search of suitable solvents for the coating in the industry sector, they are mainly using some kind of solvents to capture the carbon dioxide. They are mainly using amine. Then what is amine? Amine is derived from ammonia where one or more hydrogen atom is replaced by alkyl or aryl group. Here we can see that this is ammonia. Here this one hydrogen atom is replaced by alkyl group. This is ammonia, this is amine. And also these amines can be divided into primary, secondary and tertiary, depending on how many carbon atoms are attached to the nitrogen atom. Also, we can divide these amines into hindered and unhindered amines based on the hindering ability by the neighboring groups. In the normal cement-based material, carbon dioxide diffuse into the cement-based material and react with water and form bicarbonic acid. Then what will happen if we add the amine? Let's say this MDA is one kind of amine. If we put the amine into the cement-based material, as this is basic solvent, it will act as a proton acceptor and enhance the bicarbonate formation and hence carbonate ions. Then these carbonate ions will grab the calcium ions from the hydrated phases such as portlandite and CSH and form calcite. As amine is a basic material and it acts as a proton acceptor, it is enhancing the calcite formation. This brings me to the aim and objective of this research. As we are working on multiple groups, our team is mainly focusing on the finding a better solvent for CO2 absorption in cement-based material. To find this one, we will evaluate the CO2 absorption capacity of different amines in different calcium-rich solutions such as portlandite and synthetic CSH and hydrated cement powder. Then we will study the microstructural changes during carbonation using different amines. Finally, we will apply as a coating to study the direct air capture ability. These are the amines we selected for this purpose. First one is amino-ethyl ethanol amine. This has both primary and secondary amine. Here you can see this. This nitrogen atom is attached to two carbon atoms, so this is secondary amine. And this nitrogen atom is attached to one carbon atom, so this is primary amine. So this amino-ethyl ethanol has both primary and secondary amine. Likewise, this methyl amino ethanol MAE is secondary hindered amine and methyl diethanol amine, MDEA, is tertiary amine. Here I summarized the reaction with carbon dioxide and in the presence of water. Here we can see that MAE and MDEA forming bicarbonate ions in the presence of carbon dioxide and water. However, this primary and secondary amine didn't form bicarbonate ions, they are forming carbamate ions. So, in the cement usage, these primary and secondary amines will not form calcite, instead they will remain as ions in the phosphorus solution. So, in the carbon capture in cement-based material, we can use the MAE and MDEA. This is the experimental setup. First, we prepare the solution with different calcium-rich materials such as portlandite and CSH and hydrated cement powder with amine and water. And then we kept it for carbonation. We supplied the carbon dioxide bubbling for specific period. And then we filtered it and did the microstructural analysis for the precipitate and the pH analysis for the supernatant. And we synthesized the CSH using this approach. I would like to focus your attention on the results. Here we can see that when we increase the amine percentage until 10%, calcite formation is increasing in all the amines. However, after 10%, this calcite formation is decreasing because of the amine loss on the surface of the calcium hydroxide particles, which was confirmed by XPS and TGA results. Here we can see that MAE giving the more calcite precipitation and AEA giving the less calcite formation. As I mentioned earlier, AEA is primary and secondary amine, so they will not form calcite. And this is the effect of amine type in different calcium-rich material. We can see that in all calcium-rich materials such as portlandite, CSH and hydrated cement powder, MAE is giving the higher calcite formation. As it is hindered amine, it has higher ability to react with carbon dioxide. Also, the reaction rate is very high. And we can see that in the portlandite solution, MAE is giving more than 2 times that of control sample. However, in CSH, it is more than 4 times than that of control sample. And then we studied the XRD analysis. Here we can see that in the presence of amine, such as MDE and MAE, the sample is, we can see the aragonite formation. This is further confirmed with the SEM images. Here we can see that flower-like needle-like material is observed in the SEM images in the presence of amine. Also, pH is reduced because of the higher carbonation in the presence of amine. However, as amine is basic solvent, it is balancing the pH above 9. Then we studied the accelerated carbon capture for the MDEA amine with 10% as we got it as optimal percentage. And we exposed this for accelerated carbonation for 6 months and then split it for like this for phenolphthalein test and TGA analysis. Here we can see that the MDA samples are the faint pink color because of higher carbonation and less pH. This profile shows the portlandite and calcite percentage throughout the day. It is interesting to say that with MDA samples show the higher calcite formation throughout the day. And this calcite formation not only because of the portlandite carbonation, also the carbonation of CSH. As I mentioned earlier, because of the organic additives, the aragonite is forming together with calcite in the MDA sample. And through the XPS result, we can see that higher peak and broad peak with the MDA sample for C1S peak. This is corresponding to carbonate ions. Also, the MDA sample has some CC and CN bonding. Because of that, this is showing the not homogeneous chemical composition. However, in the N1S peak, we can see the presence of MDA in the sample. We can't see this N1S peak for the control sample. This is further confirmed the presence of MDA or protonated MDA on the surface of the powder samples. And this is the FTIR results. We can see the shift of COH bond stretching to the low value in the MDA sample because, as I mentioned earlier, the MDA is basic amine. It reacts with carbon dioxide and forming bicarbonate ions. These bicarbonate ions interact with hydroxyl group. Because of this, it is changing the electron density and the bond strength of COH bond. This leads to the shift to lower wave number of COH stretching. And this brings me to the end of the presentation. 10% amine gives the higher peak of CO2 absorption, and MA gives higher CO2 absorption than the MDEA. Also, the organic addition is leading to aragonite formation, and in the accelerated carbonation test we observed that 2 times calcite formation compared to without MDEA sample in the presence of amine. However, we are doing the same experiment for the ME, and we will do the direct air capture test. To thank the research team at Hokkaido University and Swinburne University, also Smith Corporation, for their collaboration and support. Also, I would like to extend my heartfelt thanks to Rilem for giving me this valuable opportunity to present my work. Thank you for listening.